Gaussian processes and more in artificial intelligence. This is PhDAI 730, University of the Cumberland in Kentucky, Lecture 6. And I'm your professor, Farid Muhammad. We will explore in more depth the Gaussian processes, a powerful framework as we have discussed in the earlier Lecture 5, for probabilistic modeling and regression tasks that are pivotal in AI, providing probabilistic interpretation of predictions. Gaussian processes allow models to not only predict outcomes but also provide a measures of uncertainty around those predictions, which is crucial for decision making in uncertain environments. Through practical exercises in Python, you can hands-on apply this knowledge by utilizing the libraries like gpytorch and scikit-learn. So we can and will implement Gaussian processes to model and predict outcomes based on probabilistic interpretations, as we will get into more depth. These techniques are particularly valuable in artificial intelligence for tasks such as time series forecasting, spatial modeling, and any scenario where understanding the uncertainty of prediction is or predictions are vital. By integrating kernel methods, as we discussed earlier, and Gaussian processes into AI workflows, we equip models with the capability to handle high-dimensional data and provide nuanced probabilistic insights, thereby enhancing their decision-making processes and overall performance. Why probabilistic modeling now? That's a good question. Let's get into a scenario to learn in more depth. Probabilistic modeling is essential because it allows systems to account for uncertainty and variability, which are inherent in real-world scenarios. In many situations, data is incomplete, noisy, or influenced by unpredictable factors, making deterministic approaches unreliable. By incorporating probabilities, models can provide not just single predictions but also a range of possible outcomes along with their likelihoods. This enables more informed decision making as it highlights the confidence level in each prediction. For example, in a complex environment like weather forecasting or medical diagnosis, probabilistic models help qualify risks and guide actions based on the most likely scenarios while acknowledging the potential for error. Consider a university system that uses probabilistic modeling to predict student success and dropout risks. The system analyzes various factors such as attendance, grades, extracurricular involvement, and socioeconomic background. Instead of simplifying flagging students as at risk or not at risk, a probabilistic model assigns a likelihood to each outcome, such as 80% chance of a student passing a course or 30% risk of dropping out. This nuanced insight allows advisors to intervene with targeted support, such as tutoring or counseling, for students who show early warning signs. Additionally, the university can allocate resources more effectively by focusing on students with the highest probability of needing assistance, ultimately improving attention rates and student outcomes. So AI often requires more than point predictions. Uncertainty is critical for risk assessment and decision making, as we just looked into the student's example in a university. The Gaussian processes provide both predictions and uncertainty estimates. Understanding Gaussian processes in a little bit more depth, we will continue using the university system as our example. Probabilistic modeling is essential because it allows systems to account for uncertainty and variability, which are inherent in the real-world scenarios. As we discussed in quite depth, In many situations, data is incomplete, noisy, or influenced by unpredictable factors, making deterministic approaches unreliable. So, by incorporating probabilities, models can provide not just single predictions but also a range of possible outcomes along with their likelihoods. So, Gaussian processes can be particularly valuable in this context because they provide a framework of modeling uncertainty in a structured way. For a university, as we discussed earlier, GPs can help predict not only the most likely outcome for a student but also the confidence in that prediction. For example, a GP could analyze a student's academic history and predict their future performance in a course along with the uncertainty in that prediction. This allows advisors to identify students who may need extra help even if their current grades are borderline because the model indicates a high probability of decline. By using GPs, the university can create personalized intervention plans and adapt as new data comes in, ensuring that support is provided when and where it is most needed. This approach transforms raw data into actionable insights, making it easier to improve students' success rates and optimize resource allocation. We can look at a scenario where the problem can arise, like predicting student performance and dropout risk in the university, as discussed earlier. So, at a large public university, for example, administrators and academic advisors face a persistent challenge identifying students at risk of academic failure or dropping out before it is too late, as we have just discussed in our previous slide. The university collects vast amounts of data, including grades, attendance records, engagement in extracurricular activities, socioeconomic background, and even mental health survey responses. However, this data is often noisy, incomplete, or influenced by external factors such as personal crises or financial stress, making it difficult to predict student outcomes with certainty. Traditional methods like fixed thresholds for grades or attendance fail to capture the nuance of individual students' trajectories. For example, a student with a sudden drop in grades might be struggling due to temporary issue, while another with consistently average grades might be at a higher risk due to disengagement. The university needs here a dynamic, adaptive system that can predict risks early, account for uncertainty, and provide personalized interventions to improve attention and success rates. So the university can implement the Gaussian process-based predictive system to model students' performance and dropout risks probabilistically. So the data integration and modeling is associated with this resolution. Uncertainty-aware predictions are the next step, and the third step is the personalized interventions. And fourth, last not the least step is resource optimization, that administrators can provide the resources. So with the Gaussian processes-based system, the university shifts from reactive to proactive student support, reducing dropout rates and improving academic outcomes. Advisors gain a nuanced understanding of each student's needs, while administrators can allocate resources more strategically. The probabilistic nature of GPs ensures that decisions are made with confidence and adaptability, making the university a more responsive to student-centered institution. So a collection of random variables, any finite number of which have the joint Gaussian distribution, can be looked at all the variables I discussed earlier in the university example, used for regression, classification, and optimization, the GP. Non-parametric is flexibility to fit complex data, as I just mentioned in quite depth. The GP framework model functions as distributions over possible functions. Prior distributions plus data, which is equal to posterior distribution, and predictions include mean and variance in terms of uncertainty. So if we revisit our university thing that we just discussed, where I clearly mentioned that the university can implement Gaussian processes-based predictive system. So the number one area that we can look at data integration and modeling. The GP model integrates all available students' data such as grades, attendance, engagement, metrics, and socioeconomic factors, and treats each student's economic journey as a time series problem. For example, the model can analyze how a student's grades evolve over a semester while accounting for external factors like participation in extracurricular activities or responses to mental health service. Unlike traditional models, GPs provide not just a single prediction such as this student will fail, but the probability distribution showing the likelihood of different outcomes, such as there is a 60% chance that this student will pass, but a 30% risk of dropping out if their attendance does not improve. The second step is uncertainty-aware predictions. The GP model quantifies uncertainty in its predictions, which is critical for identifying students who might be overlooked by deterministic methods. For instance, a student with inconsistent attendance might have a wide confidence interval in their predicted performance, signaling to advisors that they need closer monitoring. Conversely, a student with steadily declining grades and high uncertainty in their future performance could be flagged for immense intervention, such as tutoring or counseling. This probabilistic approach ensures that no student slips through the cracks due to the oversimplified rules. Third, we discussed was personalized interventions. The university uses the GP's predictions to design tailored support programs. For example, if the model predicts a high dropout risks for a student due to financial stress, the system can automatically recommend scholarship opportunities or part-time work programs. If a student's engagement metrics suggest disengagement, advisors can reach out with mentorship and extracurricular opportunities. The model in this situation continuously updates its predictions as new data comes in, such as midterm grades or survey responses, permitting interventions to adapt in real time. Resource optimization, which was the last not the least, by focusing resources on students with highest predicted risks and the greatest potential for improvement, the university can maximize the impact of its support programs. So I would suggest you to conduct this research in a little bit more depth to establish your understanding in using Google Scholar or IEEE Explorer. So GP regression basics are: input or training data, X and Y, and output is predictive distributions for new inputs. The role of kernels in GP: define covariance between data points, common kernels such as squared, exponential, Matrix, rational, quadratic. Let's look into this with an example in a little more depth. Let us look at a healthcare example here. A large hospital system is using Gaussian processes to predict patients' deterioration and readmission risks based on electronic health records, lab results, and vital signs. However, the current GP model struggles to accurately capture the complex non-linear relationships in patient data. For example, the model might not distinguish between patients whose vital signs are temporarily unstable due to a minor infection and those at high risk of severe complications due to chronic conditions like heart failure or diabetes. The raw data such as blood pressure trends, oxygen levels, lab results, and medication histories often contains hidden patterns that a standard GP with basic kernel cannot effectively capture. As a result, clinicians receive broad or ambiguous risk predictions, making it difficult to prioritize care or intervene proactively, the hospital needs a way to enhance precision and reliability of its GP-based predictions to improve patient outcomes and resource allocation. The applications of kernels in GP to solve this problem is our next understanding. To refine the GP's model's accuracy, the hospital can leverage different types of kernels which define how to model interprets relationships in the data. Let us say selecting kernels for different data patterns. The hospital can use specific kernels to capture the unique characteristics of patients' data. There can be a linear kernel, a polynomial kernel, or a Gaussian kernel, or RBF. So combining these kernels for comprehensive insights, the hospital can create custom kernels by combining multiple kernels to better fit the data. For example, some of an RBF kernel and a linear kernel could model both a non-linear progression of chronic diseases and the linear effects of specific treatments. This approach enables the GP to provide more nuanced and accurate risk predictions, helping clinicians distinguish between temporary fluctuations and serious declines in the patient's conditions. So by integrating kernels into their GP models, the hospital transforms its predictive system into a precise, adaptive, and actionable tool. Clinicians gain deeper insights into patient risks, enabling them to design personalized care plans that address the root causes of deterioration. The result is better patient outcomes, reduced hospital readmissions, and more efficient use of healthcare resources. The hospitals can proactively allocate interventions such as additional monitoring, medication adjustments, or specialist consultations where they are most needed. So this is, I thought to share this with you, even though I have used few kernels, but I would strongly suggest you to look at squared, exponential, Metron, and rational quadratic at IEEE Explore or Google Scholar to understand in a little bit more depth at how they work in GPs. Advantages of Gaussian processes: provide uncertainty estimates, flexible and interpretable, work well with small data sets as well, no need for explicit feature engineering. That is also a part of the thing that you must know, as I have shared with you two examples. One is the university students management system, and the other one is the healthcare system, that how we deal with the patient's data by applying the GPs and kernels. Real world uses: time series forecasting, stock prices and weather is an example. Spatial modeling is environmental data. Bayesian optimization comes handy when hyperparameter tuning happens. Robotics as path planning, as we had been discussing robotics extensively in our previous lectures in the PhDAI730 series of lectures. Predicting the future with uncertainty. Forecasting is sales or temperature, pollution levels across a city. This we can deep dive in a little bit more depth to understand. Predicting the future is inherently challenging because of the uncertainty and surrounds real-world events. Whether forecasting stock markets, weather patterns, or patient health outcomes, traditional models often provide single-point estimates that fail to capture the range of possible scenarios. This limitation can lead to poor decision-making, as it ignores the natural variability and unpredictability in data. Probabilistic approaches such as Gaussian processes, as we are discussing this in this lecture, address this issue by modeling not just what is likely to happen, but also the confidence in those predictions. By accounting for uncertainty, these models provide a more realistic view of potential outcomes, permitting individuals and organizations to prepare for multiple scenarios rather than relying on single forecast. In the fields like healthcare, finance, and robotics, the ability to predict the future with uncertainty is invaluable. For example, a doctor using probabilistic model can assess not only the most likely progression of the patient's condition but also the range of possible outcomes, including rare but critical events. Similarly, financial analysts can evaluate investment risks by considering the probability of different market conditions. This approach enables better planning and risk management, as it highlights both the most probable future and the less likely but still possible scenarios. But by embracing uncertainty, predictive models become more robust, helping users make informed decisions even in the face of incomplete, noisy data. The power of uncertainty. The uncertainty helps in risk-aware decision making. The medical diagnosis or autonomous driving, as we had been discussing in this lecture in quite depth. Practical implementation. GPs provide probabilistic predictions and uncertainty estimates, as discussed earlier. Kernels define the covariance structures, and applications span forecasting, optimization, and spatial modeling. So imagine you're trying to find the lowest point in a hilly landscape, but it's foggy and you cannot see everything at once. You write a Python code using a smart method called Bayesian optimization to guess and check where the lowest point might be. Instead of randomly searching everywhere, it uses math to make educated guesses, learn from each try, and gets better at finding the best spot over time. The code you wrote in this hypothetical scenario by defining a simple hill, a math function, and sets of range like from 0 to 10 to search the lowest points. After a few tries, it tells you the best spot it found and how low the point is. This method is super useful in real life for things like tuning machines, designing experiments, or even helping robots learn. These last three Imagine slides, I would suggest you to try writing a Python code and see how it fits and how it gives you certain outputs. Happy learning. See you in the next lecture.